is actually moving. So that was the definition of current. And so we talked about the invisible, right? We talked about invisible energy that we are surrounded by ourselves, the movement of electrons. So talking about this without any quantification is meaningless, right? Because at the end, we still need to follow some rules, follow some path in order to quantify them. If we cannot quantify them, we cannot use some numbers, how we are going to explain the fact that some kind of electron or some kind of one material has some energies that are going to move aside, how we can going to talk about it. That's why we do have a Coulomb's law. We are going to use that one in order to quantify the energy. But just before talking about that, we have to have specific and strong definition of Coulomb itself. Let's talk about it. So what is Coulomb? The unit that we use for electric charge is something we call as Coulomb. And what is the charge of a single electron? Right now we are talking about the single electron, is an incredibly small but precisely known value. And we something call it as 1.6 times 10 to the power of negative 19 Coulomb. It means that movement of only one electron one way to another way is only going to change the charge or going to change the concept of material by this number, which is so small. But remember, we are not talking about only one electron. We are talking about millions and millions of electrons that were moving one side to another. So by knowing the fact that inside our copper wire has lots of movable electrons, we can quantify them or we can times them by something. So this is something as we call a coulombs. It means that the Q or the negative, some kind of the charge that is going to absorb, that's going to being absorbed or some kind of being lost by specific materials is going to be the energy of that specific electrons times n, which is the number of electrons. Why we do have this negative sign? That makes sense because as I just told you, whenever a material is absorbing electrons, that guy is going to have negative sign or has a negative charge. At the same time, when losing that, is going to have positive charge. But right now, we're assuming that the material is going to absorb the negative signs. So N is the number of electrons. E is the charge or some kind of this specific number that we know about the charge of electron, 1.6 times 10 to the power negative 19. And Q would be what? The total charge that is going to be negative itself. So 1 coulomb of charge, it means that if I do have this specific guy as 1 coulomb, remember that right now for each specific charge, we do have this number of coulombs. N doesn't have any unit. This guy is coulomb and this guy is going to be coulomb as well. The 1 coulomb of charge represents the excess charge of approximate of these amount of number, 6.24 times 10 to the power 18. How we found this number? If you divide 1 by that 1.6 times 10 to the power negative 19, you would have this number. This guy will tell you that how many some kind of electrons you need in order to change the charge only by 1 coulomb. It means that you have to have 6.24 times 10 to the power 18. This is a huge number of electrons if you would like to change some kind of the charge only by 1 coulomb. And it's an enormous amount of charge at the atomic level itself. So let's see an example, right? So far we were talking about how we actually are going to use that or quantify that. So why not solving an example? Imagine that I do have an object. And this guy is going to gain 3 times 10 to the power of 12 of electron through a friction. Something is happening and this guy is going to get that specific number of electrons. What is the total electric charge in coulombs itself? Simple. We know a formula for that, right? Q is negative N times E. We know this number. Try to memorize that one, or most of the time you can ask your instructor or your professor, or maybe in the exam, they're probably going to mention that, but this is a number it would be better to memorize. So 1.6 or 1.602 times 10 to the power negative 19 times your guy, your N, and times a negative because you do have a negative sign itself. So if you do this calculation, and some kind of adding all of those exponents rather than me, the Q is going to be negative 4.8 times 10 to the power negative 7. It means that something related to negative 0.48 microcoulomb. What is micro? Micro is 10 to the power of negative 6 itself. So at this point, we say that after moving all of those electrons from one material to another one, my guy or my material only got charged by negative 0.48 microcoulomb. And the object gained electrons, which are going to be negative, obviously, so the final charge must be negative, and the sign completely makes sense. So let's talk about the Coulomb's law. So far, we were talking about the Coulomb. Let's talk about prediction of attraction and repulsion. So right now, we know something about Coulomb. We know that each material is going to be charged or discharged based on a specific number, that the Q is going to be negative or positive based on the absorption of electrons or losing the number of electrons. So what would happen if we do have two materials that each of them, they do have a specific number of Q, Q1 and Q2? We would like to find the energy between them. We would like to see that how much energy or how much force to this specific, that we know the force and mechanical electrical force as a unit measurement by Newton. How much Newton they are exchanging between themselves, and also are they going to absorb, are going to repel each other. We are going to quantify that specific force using the Coulomb's law. The Coulomb's law would says that F is going to be equals to K times the absolute number of Q1 and Q2. Right now, we don't care about a specific sign, positive or negative. We are just taking care about the absolute number itself. The negative N1 times E, and Q2 negative N2 times E. Divided by R2. R is the distance, and we are going to use the power 2 of that specific things. So far, F is going to be my force, something that I'm looking for. Q is the amount of charge that at each object, which is going to be in coulombs. R is the distance in meters. It probably is going to so small, because we're talking about when we're making two objects very close to each other, so the R should be small, but we have to make sure that R should be in meters. And Q is a constant. This guy is the Coulomb constant and is the fundamental value of the nature. The K, again, is a number that it would be better to be memorized. It's 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb to the power 2. This is a unit for that. So another thing that we have to know, rather than just quantifying this, obviously we are going to find a number based on the information the question will give it to me. We have to determine direction. If the signs of Q1 and Q2 are the same, means that the force is going to be repulsive. Those two things are going to repel each other. On the other hand, if the sign of Q1 and Q2 are opposite, those forces are going to attract, or those specific objects are going to attract each other. Let's have an example. So calculating the force between charges. Imagine that I do have two small objects and are separated by a distance. This is going to be distance. Their charges are Q1 is this one, is Coulomb, 2 Coulomb, and Q2 is this Coulomb. Find the magnitude and direction of the force. Obviously, the very first thing that we can find is the direction of the force. What is the direction of the force? Because one is positive and one is negative, they are going to absorb each other. This is a fact. Another thing that we have to do is just write down everything we have in our hand. The Q1 is going to be 2 microcoulomb. So 2 times 10 to the power negative 6, by the way, is positive. And then this is going to be Q1. The Q2 is with negative 3 times 10 to the power negative 6. So we know that. And then we have to just put all of those numbers in the Coulomb's law. F is going to be K, this is 8.99 times 10 to the power of 9, multiplied by Q1 times Q2. Again, we don't care about the sign because we do have the absolute value, divided by R to the power 2. If you calculate that, you have 21.6. What is that? It's the force between those two. It means that the charges are going to have opposite sign. First of all, we know that, so they're going to attract each other. They pull forward each other with a force of 21.6. It means that if you do have two objects, they're going to pull each other with that 21.6 Newton of force itself. So let's talk about using the knowledge that we just earned related to moving charges from one object to another one and having the maybe different or opposite charges that they're going to absorb or to attract each other, and maybe we are going to make two same kind of charges that they can repel each other in an actual world. You already saw that without even you know it. Like rubbing the balloon in your head, and sometimes if you do that, you see your balloon is going to stick to your head. Actually, again, that it's about electrical circuit. It is about the movement of electrons and movement of the charge. So let's see what's going on actually. So the most static electricity that's going to cause this kind of things around ourselves is going to because something we call as triboelectric effect. What does it mean, triboelectric effect? It means that transferring electrons from one material to another one by rubbing them together. Just rubbing the balloon and the hair itself. If you rub a balloon on your hair, the balloon is going to gain electrons and it's going to be negative. So on that side, your head or your whole body is going to lose electrons and it's going to be positive. Since they're going to be opposite, they're going to attract each other. Comb then paper, run a plastic comb through your hair to charge it. By charging that, actually you're giving electrons that plastic material, and that guy is going to be negative. In the meantime, if you make it close to a stick of papers, they're going to absorb each other, because at the beginning the paper was neutral, but after some times the paper is going to gain positive side, and this negative and positive are going to absorb or attract each other. So this is something that we call as polarization, charge separation within the paper itself, right? At this point, the negative and positive side are going to be at one side and another side. So at this point, if you make it close to this guy, they're going to absorb each other. The tape trick. I'm going to press two pieces of tape firmly onto a desk, then quickly rip them off. They will likely repel each other because they both gained a similar charge, right? Both of them, they do have negative part, and if you rip them off and if you try to make them close together, it is something like a magnet that you're trying to make negative and negative side of the magnet, both of them together, and see that they're going to repel each other. So by the way, be careful. Not all of these experiences are going to be safe. Some of them are a little bit dangerous, so be careful with that. So let's talk about the real world application again and some kind of awareness. The key application is something we call it as the electrostatic discharge. What does that mean? The mini lightning shock you feel from the doorknob can carry thousands of volts. I believe you all see that. Sometimes it would be so annoying, especially when you are trying to open up the knob and you had some kind of a jacket on your side, and because of all those charges that you had, and you are going to connect your hand to the doorknob, is going to be discharging of so many electrons in a very, very short amount of time. It could be thousands of volts, and this is not that kind of dangerous itself, but a discharge you can even feel, right? Because it's going to be destroyable. What does that mean? This guy is going to carry a lot of voltage and could be so dangerous for electronic devices. These electronic devices are so sensitive against this amount of voltage, and you have to be careful while you're working with that. You have to use what you have to do, the ESD, or you have to connect your hand or some wrist straps and mats in order to make sure that electrode, some kind of charge, is completely discharged before touching them, to not having any damage or any effect overall on that specific electronic thing. The semiconductors. This ability is some kind of the ability to precisely control the charge flow in the materials like silicon is the foundation of every computer, smartphones, and modern electronic devices. If you guys remember, semiconductors was a specific kind of material that you had control over those guys in order to be insulators or conductors itself, and those guys are so vast, common use, and powerful itself. So about DC power, you see it everywhere. The batteries, the phone chargers, and car electric system all are common examples of direct current. When we say that direct current, it means that the specific voltage that those guys are working is going to be constant all the time, and this kind of system is going to be governed by all of these principles. If you remember, when we were talking about the current, we started this fact that we are going to connect the battery itself with the load. But you have to be very careful, because you have to treat any device that plugs into a wall and outlet as something is going dangerous, and you shouldn't open them because of everything that we know, because of electrostatic, or even because of the fact that these guys contain DC voltage, and we are going to talk about in the future those guys are dangerous. So be careful when you're working with them. Never connect the terminals of a battery directly together. It means that batteries have positive and negative side. You shouldn't connect these two guys using a wire, because something happened, as we call it, as a short circuit. And short circuit means that the current is going through this wire that would be so much, and since the resistance that you have inside the wire, or something we call as var, is so low, the current is going to be so high. So it's going to cause some sparkles, it's going to melt the wire, and even if your hand is touching that one, is going to cause a very dangerous situation. When handling the circuit boards, ground yourself by touching a large metal object first. Why? As I just told you, our hand could be carrier of so many charges or so many electrons. So by touching our hand, that specific electronic device, we are going to discharge thousands of volts in a very, very short amount of time. And this one could be deadly for our electronic system itself. So let's talk about the summary. What we learned. All electrical behavior is driven by the movement of electrons. Electrons are the essential of our system, of our electrical circuit, or any kind of electronic devices that we have around ourselves. We learned something about the valence electrons. Means that those guys would be at the end of each atom, and they are going to determine if a material is a conductor, insulator, or semiconductor. And we learned that charge is going to be measured in Coulomb. One electron has a charge of 1.6 times 10 to the power negative 19 Coulomb. We learned about the Coulomb's law. F is K times Q1 times Q2 divided by R2, and this one is going to allow us to calculate the force between the charges. So right now I put a couple of practice questions for you, so you can look at them, and by using everything that you guys learned so far related to electrical circuit knowledge, you can find the power when there's some kind of force and anything related to that. After that part, let's just try to solidify and continue our some kind of work itself. Again, remember that when we are talking about the charges, if both of them are going to be positive, means that those guide, or the force that we have, is going to be repulsive, while if one is positive, another one negative, is going to attract each other. Another thing that we learned is about the microcoulomb to coulomb. So as you just learned, micro is 1 times 10 to the power negative 6. By knowing that, it's going to be very usable most of the time. We can convert the microcoulomb to coulomb. And F, or the force that we do have in order to find the specific Newton, or the force among the two charges, follows this formula. K is going to be constant, or the constants, times Q1, Q2 divided by R2 itself. So today we talked about the fact that how we can use the electrical circuit, the charges, anything related to that, not only in the quantification, but also in the main usage of our day-to-day life. I would like you guys to completely understand everything by rewatching this video and making sure that you completely comprehend and digest everything related to that. Because from now on, all of the subject is going to be serious. After that, after this specific subject, we are going to touch the very main part of electrical circuit, which is about the Ohm's law, the connection between resistor, voltage, and current, and then we are going to enter the whole world of electrical circuit. Thank you guys for being here with me. Don't forget to like, share, and comment. Have yourself a great day, night, whatever. See you around.